Hey friends, it is Ben again. This is a video for the Calc 1 class because we didn't quite finish up all the L'Hopital's rule examples that I had in mind. So let's just go right to it and see how that goes. So please bear in mind, I happen to be doing this during office hours, so I might have to stop and start the video if somebody comes by. All right. So the next example that we didn't get to, if you recall, the last example that we had was log x times inverse tangent of x. X is going to 0 from the right, and it turned out to be a real bear, right? But for this next one here, it's one of a different variety. So if you plugged in your x going to infinity here to this part, you know that that's going to 1. And this power that we have here is going to infinity. So if you have 1 and you put it to any power, you ought to get 1. But if you've got anything that's even slightly larger than 1 and you put it to the infinity power, it ought to go to infinity. And if you get anything even slightly smaller than 1, then it ought to go to 0. So we've got that indeterminate form coming up there. And I went ahead and wrote down here on the side the various indeterminate forms. We've already encountered 0 over 0, infinity over infinity. And we know that when you have 0 times infinity, you turn that into either 0 over 0 or infinity over infinity, whichever one's easier to take the derivative of, right? And the infinity minus infinity, it's always a do the least common denominators sort of problem. And then you have to figure out how to make it into 0 over 0 or infinity over infinity. Okay. But now we've got these three sorts of things here with exponentials. If you have something which has 0 to the 0 power, every example that I can make up that's easily doable ends up being 1. But I need you all to keep in mind that the point of having you do these problems is not to get the answer. I know the answer. The point is for you to demonstrate to me that you can do L'Hopital's rule. So that's the thing that's going on there, okay? But so 0 to the 0, expect the answer to turn out to be 1. But this 1 to the infinity problem, the answer always ends up having something to do with e. And this infinity to the 0 sort of thing can turn out to be anything, really. But often, again, it has something to do with e. So keeping those in mind, we look over here and see that we've got a problem that is one of these 1 to the infinity type problems. And so let's see how you tackle one of those, all right? So the main trick is remembering this. E to the log x is just x. Those are going to cancel out. So when we're doing this sort of problem that has exponents in it, we're going to take advantage of that. And we're going to say that this is equal to the limit as x goes to infinity of e to the ln of this stuff. Okay. And that's the limit as x goes to infinity, e to the power. Now, logarithms have the special property that you can pull the exponent out. So we'll have e to the x ln of x over x plus 1. There's a couple of things that you can do to simplify on this. And I'm going to put this note here that you could rewrite the stuff inside the parentheses. as this, but you're probably not going to spot that, okay? If you do spot that, the derivatives we're going to deal with become slightly easier. But if you don't spot it, then you have to deal with what you've got in place. So let's go ahead and work with it as though we didn't spot that. But what we do spot is that this is going to go to infinity. This is going to go to 1, and that the log of 1 is 0. So that means that this has turned into a infinity times 0 type problem. Okay. So do you see how this is it feels pretty messy, because you start out with a 1 to the infinity and you turn it into an infinity to the 0, or infinity times 0, which you'll have to turn into either a 0 over 0 or a infinity over infinity, and infinity over infinity. Well, so what we're going to do is, keeping the e there, I want to do the log of x over x plus 1 divided by 1 over x. The reason I want to do that is that I think the derivatives will be less miserable. Not easy, less miserable, okay? So when you plug in here, you can see that you've got a log of 1, which is going to 0, and the bottom is going to 0. So we've got L'Hopital's rule, 0 over 0 case, limit as x goes to infinity, e to the, now we take the derivative of the top and the bottom, okay? The bottom is relatively easy. We did the derivative of 1 over x in class today. The top, however, you've got to say, I want to take the derivative of a log. So that means I will have 1 over the thing that's inside the log, which is this x over x plus 1, then times, now the chain rule says we have to take the derivative of the x over x plus 1. So if you did that simplification that I suggested up there, this would be super easy. But if you didn't spot it, then you've got to use the quotient rule. Quotient rule says take the derivative of the top, leave the bottom in place, or leave the bottom alone, but as a factor, minus. Now we leave the top alone and take the derivative of the bottom, divided by the bottom squared. Yuck. All that over the derivative of 1 over x is negative 1 over x squared. Goodness. Okay, so I am going to need to add yet another page on here. And I'm going to copy this. And I'll make it bigger so that it's easier to see on the screen. Okay. All right. Equals limit, x is still going to infinity. All right. E to the power. Okay, so you see this 1 over x plus 1. That's just going to be x plus 1 over x. Okay, just flipped it over. Times, now you see this here, we've got x plus 1 minus x. So we're going to end up with just a 1. And we have an x plus 1, the quantity squared, times, now this part here will get a negative. I hope it doesn't bother you that I write it to the front instead of the back. The negative 1 over x squared, so it'll be just an x squared. Now, fingers crossed, when we start doing cancellation, I think things are going to get nicer, all right? So we can see that we cancel the x plus 1 with one of those x plus 1s. we cancel the x with one of those x's. And then we say limit as x goes to infinity, e to the power minus, there's still an x for the numerator and an x plus 1 for the denominator. Now, if you want to use L'Hopital's rule again, because we get infinity over infinity, you can totally do that. But this piece here is a fraction with the same power on the top and the bottom. So we're going to end up with an e to the minus 1, okay? Or if you prefer, 1 over e, either way, okay? Pretty messy, but it's doable, okay? All right, let's tackle another one here, okay? So let's talk this through first, and then I want you to pause and try this on your own. So we've got the x going to 1 from the right, okay? And that means when we plug into the log, we are going to be getting a 0. Now, since it's coming from the right, it's a little more than 0, but but it is going to 0. And so 1 plus that log must be going to 1. And this power that we've got up here, 1 over, so x minus 1 is going to 0, but it's 1 over that. So it's going to either plus or minus infinity. And because the x is going to 1 from the right, this is going to plus infinity. So what we've got as a form here is a 1 to the infinity type of thing, okay? So if you're looking at that and saying, aha, but my ln x is a little more than 0, so this is a little more than 1, and this is going to infinity, therefore I'm going to be having an answer that goes to infinity. Unfortunately, that sort of reasoning usually doesn't work. Sometimes it does, but usually it doesn't. So we got to tackle this using L'Hopital's rule and see where we go. And remember, L'Hopital's rule is really designed for 0 over 0 or infinity over infinity. So we're just trying to get to that stage, okay? So we're going to remember the last example, which had us take e to the log of that stuff. So 1 plus ln x to the power of 1 over x minus 1. So that's equal to the limit as x goes to 1 from the right, e to the power 1 over x minus 1, ln of 1 plus ln x. And if you're saying, weird, log of a log, yeah, it's going to be messy. But now when we try to plug in, this is going to, what's that going to? Positive infinity. And this is going to 0. So we should be able to get this. My e doesn't need to be that big. Okay. Into log 1 plus log x over x minus 1. Okay. Now when we plug into these, the top is going to 0 and the bottom is going to 0. So we are totally in the case of 0 over 0. And we can go ahead and apply L'Hopital's rule. So the bottom is going to be super easy. So let's worry about the top. So on the top, you will have 1 over the stuff inside the parentheses times, now the derivative of the stuff inside the parentheses is 0 plus 1 over x, right? And then all that divided by the derivative of x minus 1 is just 1. So tidying up here, x is still going to 1 from the right, e to the x 1 plus ln x quantity 1. All right. So as x goes to 1, and we plug in there, the top is going to just 1. So probably not going to be L'Hopital's rule again. The bottom is going to be going to 1 times 1. So yeah, we're done with our L'Hopital's rule. We get to actually just plug in e to the 1 over 1, which is just e. So yeah. And e, as you know, is a number, it's like 2.7 or something like that. Okay. That's what we're looking at. Yay. All right. Now let's tackle another fun one here. Again, let's talk through it, and then I want you to pause and give this a shot on your own. So for what we're tackling here, we talk through it and have an x to the sine x. As x goes to 0, well, of course, the base is going to 0, but also the exponent. So this is going to be one of our 0 to the 0 type problems. And anytime it's one of those exponential things, you use the e to the log trick. Okay. So we're going to write down here equals limit as x goes to 0 from the right, e to the ln x sine x, x to the power sine x, sorry. And that is the limit as x goes to 0 from the right of e to the sine x times ln x, okay? So if you plug in there, you've got 0 times infinity, right? So one of these things needs to go into the denominator. I'm not really entirely sure which one. I'm going to try putting the sine x into the denominator, but you might want to try doing the ln x. The reason I'm thinking that I'll try the sine x is that we tried putting 1 over ln x in that arctangent problem, and it got really messy. So I'm thinking this time maybe we do the other. All right. So again, pause and try this out. And then as you come back here, we're going to try limit as x goes to 0 from the right, e to the power ln x divided by, and I'm going to go ahead and write it as cosecant x, which is, oh man, that was weird. Cosecant x, which is 1 over sine x, right? And then as I plug in, I see that I'm getting infinity on the top, infinity on the bottom. So I'm going to go ahead and use L'Hopital's rule with the infinity over infinity case. Take the limit as x goes to 0 from the right, e to the, okay. So the top is relatively easy. Derivative of log x is 1 over x. And the bottom, derivative of cosecant, you may have to go look this up, right? Minus cosecant x cotangent x, okay? All right, I don't like that at all, so I'm going to try to rewrite it where it's stuff that I'm more used to. And so I'm going to flip things over. I'll have an e to the minus sine x tangent x, and then the x downstairs. Now, the great thing about that is that if I group here, I know what that limit is. And the rest of it is going to be not too hard to deal with. So I'm going to say e to the minus 1, and tangent of 0 is just 0. So we will end up with a 1 as an answer there. If you recall what I said earlier, all of the nice examples with 0 to the 0 turn out to be that. So I don't want to create something just to show you that it can turn out to be something else. It can, but they're always horrible. So, all right, let's tackle this one. This is our last one, all right? So pause just a minute and like write this down and see what form is it and what do you want to do, and then come back and we'll talk more. Okay, so when you plugged in there with your x, since x is going to infinity, it's got to be the infinity to something, and that 1 over x squared portion must be going to 0. So this must be an infinity to the 0 type of problem. So infinity to the 0. That's, again, one of our indeterminate forms. If you had had 0 to the infinity, that's not indeterminate. That will just be 0. But infinity to the 0 could turn out to be anything. Okay. All right. So for this, because it's an exponential type form, we'll go ahead and rewrite it. And we're going to have an e to the ln of x to the 1 over x squared, like kind of like the previous ones. And so just a rewrite here, we will have e to the, I'm going to write ln x over x squared. That's, pulling the 1 over x squared out front and then putting it together there. So pause for a second, try to decide what is the case on this. Okay, so then you came back, and log of infinity we think of as infinity, and infinity squared we think of as infinity. So that means we get to use L'Hopital's rule, but it's the infinity over infinity case. All right. So we've got e to the power, applying L'Hopital's rule. The derivative of log x is 1 over x. The derivative of x squared is 2x. So we have the limit as x goes to infinity of e to the 1 over 2x squared. As x goes to infinity, this stuff in here is going to go to 0. So we have e to the 0, or just 1. Okay. So I hope that has y'all covered for this sort of thing. Please bear in mind, the point is not getting an answer. The point is doing the work in between, because insofar as getting an answer, we can always do that using a calculator or some sort of graphing utility or something, right? But that work in between, you need pieces of it in order to understand other things that might come up in a later class. So, all right, I'm gonna let you go, and I will talk to you again on Friday. Hopefully not with a video. Hopefully we'll just be, we'll just get through the material Friday, hopefully.